Hello, welcome to this video produced as part of the Further Maths Support Programme's material for A-Level Maths and Further Maths. This one continues the series on impulse and momentum in 2 dimensions. And in this session the focus is on oblique impacts. Previously we've looked at the direct impact of 2 particles or spheres. Now we look at the oblique impact of 2 spheres. In a moment or two I'll make clear what oblique means. We'll make several assumptions. The first is that the spheres are uniform and smooth. The second is that the spheres have the same radius. And the third is that the spheres move without rotation. When 2 spheres collide, at the moment of impact, that defines a line of centres. Now the diagram makes it look as if the line of centres has to be in our field of view across the screen from left to right, but of course it's perfectly general. All we're agreeing is that we turn the picture around so that it looks that way. So that representation is perfectly general. So we have a line of centres. Now once we've got that, we immediately take the velocity of A shown, B is stationary, and that line of approach of A is at an angle to the line of centres. That's what we mean by an oblique impact. Now we take the axes in the usual way. The x-axis is defined by the line of centres and the y-axis is fitted in to match. So that's our general situation for this particular model. Now the first thing to realise is that sphere B will move off along the line of centres. Now why is that? If you consider what's going on in the impact, you've got 2 spheres in contact. Now as usual I'll draw a gap. And what can we say about the impulse between them? Well, it has to be along that line of centres. If it weren't, there'd be some other force that's tangential to one of those spheres or the other in the y direction, positive or negative, and that would imply friction, but we've agreed that our spheres are going to be smooth. So as a result, the impulse between the 2 of them can only be along the line of centres. Now that means, from the point of view of B, that the initial velocity with which B moves has to be in that same direction along the line of centres. There isn't any impulse to give it a movement in any other direction. Now for A it's a little more subtle. There can be no change in momentum along the y-axis for the same reason, because there's no impulse, and that means that the velocity component tangential at the point of contact, perpendicular to the line of centres, that tangential component, the one in the y direction, must be unchanged. So we take 2 things from this situation. Firstly, that B moves off along the line of centres to the right, and secondly, more difficult to show until we start to put figures in, the component of A's velocity perpendicular to the line of centres is unchanged during the collision. So we can look at the motion parallel and perpendicular to the line of centres. That's implied by having our axes. In both cases moments are conserved, and we've just discussed specifically what that means. So there we have a picture which represents what happens afterwards. After, we've got the velocity of B shown along the line of centres, and afterwards we can at least say that the component of A's velocity is unchanged perpendicular to the line of centres. Okay then, so we're now going to adopt a convention of representing a collision in 2 diagrams. The upper diagram shows the position just before, and the lower diagram shows the position just after. So let's go through that one thing at a time. First of all, we get the x-axis along the line of centres, which gives us our axes. Secondly, we're saying that B is initially not moving, so that's the velocity for B shown, and the velocity of A is oblique to the line of centres, and we show that by the general expression uv. All we're really insisting is in this case that V is not 0. That would make it along the line of centres. Now for afterwards, first of all we're agreed that the B moves off along the line of centres, so that means that B's form is most generally expressed as x with a 0 component for the y-axis, and then the subtle point that for A, the conservation of momentum perpendicular to the line of centres means that the component of velocity of A in that direction is unchanged. So we show A like that. We'll see that U has changed to minus W because I've got my arrow swinging over towards the left, and V is unchanged from what it was before. So that's the general situation. So now let's look at a particular problem where we've got spheres A and B of masses m kilograms and 2 m kilograms. Before the collision, A is moving with speed 4 meters per second at an angle of 60 degrees to the line of centres, and B is stationary. That's exactly the scenario we've just been considering. The coefficient of restitution is 0.25. So we want to find the speeds of A and B immediately after the collision. So we take our axes from the lines of centres. We take B as not moving, and we introduce the velocity of A as described in the question. It's coming in at 60 degrees to the line of centres, and it's got magnitude 4. So if we resolve that velocity into two components, we'll get 4 cos 60 and 4 sin 60 for the two components, and taking as usual that cos 60 is a half and sin 60 is root 3 over 2. Now the information there will go into the diagram which shows what happens before, and we'll have to add in our unknowns for what happens afterwards. So there's the position before in the upper half of the diagram. We put in the two velocities transcribed from the previous slide. That's what we agreed. And below we have to introduce the velocities afterwards. Now we agreed that the y component for the A velocity is unchanged, and the B velocity shows that it moves off to the right, so there's no y component. Now armed with that, we can then apply momentum, and we've applied momentum perpendicular to the line of centres already. That's how we got that B moved off to the right and that A's the y component is unchanged. So we apply it now parallel to the line of centres, so we'll have 2 times m. That's this 2 combined with this m, added to 0 for the momentum of B in the x direction, and that will give us similarly the v by itself because there's just an m, well mv, and then we'll have 2m times x, which is the momentum afterwards. So that will simplify to 2 is equal to v plus 2x. And similarly, we'll have Newton's law of restitution. Now that's only to be applied along the line of centres because that's where the collision takes place. That's where the impulse of the collision acts, I should say. So that will mean that that e times the velocity of approach, which is simply the 2 component of the one I've circled here, I'll circle it again, that 2 times 0.25 is equal to the component of separation, which is x minus v. Now that equation 2 will simplify, as we'll see in a moment. So there are the two equations which we've just obtained, and they'll simplify. The first one will give us, we can cancel the m's, so we'll get 2 is equal to v plus 2x, and the second one will simplify by multiplying by 2 right through, so that the left hand side becomes 1 is equal to 2x minus 2v. So there we are, those are two equations. So now we can see that we can solve them. The simplest way to solve is to subtract the first one from the second. So that will give us 1 is equal to 3v. So v is equal to 1/3. That's a third. And so if we substitute that into the second equation, that will tell us that 2 is equal to 1/3 plus 2x. So if we multiply by 3, we get 6 is equal to 1 plus 6x. So clearly from that, x is equal to 5/6. So our two unknowns, the v and the x, are now given by the values we've just found. So on the next page we'll see that lower diagram, the after diagram, with those two numbers substituted. So there's our calculations, and now we move to a picture which has those values included. So that's just the transcription from the previous slide of the values with the answers in. So now we have to find the speeds of A and B. Well, the speed of A is just the magnitude of the vector that we've got there. So that will be the square root, the usual Pythagoras calculation, of 1/3 squared plus 2 root 3 squared, which gives us the square root of 1/9 plus 12. Well, 12 and a ninth is 109 over 9. So 109 over 9 square root. And the speed of B is trivial because that's just got a single component, so that will be 5/6. So there's our calculations. The speed of B is 5/6, as I just said, and that's turned into a decimal. The calculation I got as far as the square root of 109. It was over 9, but that was when the 9 was under the square root sign, and that works out again as a decimal. So we can now quote the answer to an appropriate degree of accuracy, and that concludes that calculation and this particular video. The next one is on oblique impacts, where the sphere B, if we can still call it that, is moving rather than stationary.